Imagine you're in the fastest spaceship ever built, pushing toward the speed of light. But the closer you get, the heavier your ship becomes, and time itself starts to slow down. It's as if the universe has an invisible wall that nothing can ever break through. So tonight, we're going to find the answer to one question: why nothing can go faster than the speed of light. Where in the world are you right now? And is the sun up? Or have the stars come out? If this cosmic mystery pulls at your curiosity, stay with me. Maybe leave a subscribe drop, a like, or just let yourself fall into this journey. Now let's begin. Here's something unsettling. You've never actually seen the present moment. Everything your eyes show you is already the past, a ghost of something that happened nanoseconds, minutes, or even years ago. Right now, as you look at your hand, the light bouncing off your skin takes about 3/1000th of a second to reach your eyes. It's an incredibly tiny delay, but it's real. You're seeing your hand not as it is, but as it was 3 nanoseconds ago. Look up at the sun on a clear morning. That warm light on your face. It left the sun's surface 8 minutes and 20 seconds ago. The sun you see is the sun of the past shining from a moment when you were doing something completely different. Maybe still asleep, maybe finishing breakfast. If the sun suddenly vanished right now, you wouldn't know for more than 8 minutes. You'd keep seeing it, feeling its warmth, completely unaware that it was already gone. And the stars, those tiny points of light scattered across the night sky, are even more ancient. The light from the nearest star, Proxima Centauri, takes 4.2 years to reach us. When you look at it tonight, you're seeing it as it was 4 years ago. Look at more distant stars, Betelgeuse, Rigel, Deneb, and you're looking 10 hundreds, even thousands of years into the past. Some of those stars might have already exploded, their light still traveling toward us, carrying the image of something that no longer exists. We live in what you might call a continuous past. There is no universal now that we can see. Every photon that enters your eye is a messenger from history, and the farther away something is, the older that history becomes. This isn't philosophy or poetry. This is the fundamental nature of perception itself. But for most of human history, nobody knew this. For thousands of years, people assumed light traveled instantaneously. You open your eyes and you see immediately, without delay. It seemed obvious. Aristotle never questioned it. Galileo tried to measure the speed of light with lanterns on distant hilltops, but his experiment failed because light was far too fast for his methods. Even Isaac Newton, who revolutionized our understanding of motion and gravity, didn't seriously investigate whether light had a speed at all. This belief made sense to them. The world felt immediate. When you look at something, there's no noticeable gap between opening your eyes and seeing the moon, the mountains, the face of another person. Everything appears instant. The universe seemed like a static painting, with light acting as an instantaneous bridge between object and observer. Why would anyone think to measure the speed of something that seemed to have no speed at all? And yet, hidden beneath this everyday illusion was a truth waiting to be discovered. A truth that would eventually reshape everything we thought we knew about space-time and the fabric of reality itself. All it took was one man with an obsession for precision, a tedious job, and a mystery in the night sky. But this story really begins not with a theory, but with a puzzle one that appeared in the careful observations of Jupiter's moons. In 1676, a young Danish astronomer named Ole Rømer was given what seemed like a straightforward task. Working at the Paris Observatory, he was assigned to carefully observe Io, one of Jupiter's moons. This wasn't just academic curiosity, there was a practical goal. Sailors navigating the open ocean desperately needed a reliable way to determine their longitude, and astronomers thought they'd found the answer: a cosmic clock. Io orbits Jupiter with remarkable regularity, exactly 42.5 hours per orbit, like the most precise Swiss timepiece ever made. Every orbit Io disappears behind Jupiter in what's called an eclipse, then reappears on the other side. If you could predict exactly when these eclipses would happen, sailors anywhere in the world could use them as a universal time reference. Compare the predicted time with the local time, and you'd know your position on Earth. Simple, elegant, perfect. Rømer took his job seriously. Night after night, he meticulously recorded every moment when Io vanished behind Jupiter's massive disk. He built detailed tables predicting exactly when each eclipse should occur, and at first everything worked beautifully. His predictions were spot on. The cosmic clock was ticking perfectly. But then something strange started happening. The predictions began to drift. Not randomly, but in a systematic, peculiar pattern. When Earth was closer to Jupiter in its orbit, Io appeared to emerge from behind Jupiter earlier than predicted. When Earth was farther from Jupiter, Io appeared later, much later. The maximum difference was about 22 minutes, an enormous discrepancy that couldn't be explained by any error in measurement or calculation. Rømer documented this pattern obsessively. Over months of observation, the timing would shift back and forth with Earth's position relative to Jupiter. When Earth and Jupiter were on the same side of the Sun, separated by about 390 million miles, the eclipses happened on time. 6 months later, when Earth and Jupiter were on opposite sides of the Sun, separated by about 580 million miles, the eclipses were running 22 minutes late. And then, gradually, as Earth continued its orbit and moved closer to Jupiter again, the timing would catch up. Most astronomers assumed there was something wrong with Io itself. Maybe its orbit wasn't as regular as they thought. Maybe Jupiter's gravity was doing something unpredictable. Maybe their calculations were off. But Rømer saw something different. He had a flash of insight that would change everything. What if Io wasn't misbehaving at all? What if the moon was perfectly regular, orbiting Jupiter like clockwork exactly as predicted? What if the problem wasn't with Io, but with light itself? What if light didn't travel instantaneously, but took time to cross the distance between Jupiter and Earth? Think about it. When Earth is farther from Jupiter, light has an extra 190 million miles to travel to reach us. If light takes time to make that journey, then we'd see the eclipse happen later. Not because it happened later, but because the light announcing it took longer to arrive. It's like getting a letter from someone far away. The letter was written on a specific day, but you don't receive it until days later. The event and your knowledge of the event are separated by the speed of the messenger. Rømer did the math. If a 190 million mile difference in distance equals a 22-minute difference in timing, then light must travel at roughly 140,000 miles per second. This was a bit lower than the true value of 186, 282 miles per second, but considering the crude tools available in 1676, it was remarkably close. He had measured the speed of light using nothing but a telescope, a clock, and careful observation of a moon orbiting another planet. The reaction was mixed. Some scientists were amazed. Others were skeptical or outright dismissive. The speed Romer calculated was almost incomprehensibly fast, far beyond anything humans had ever experienced. How could you even imagine something moving 140,000 miles in a single second? But Romer's evidence was solid. This was the first real measurement of light's speed, the first concrete proof that light was not instantaneous, but traveled at a finite velocity. This discovery shattered a belief that had persisted for thousands of years. Light wasn't magic. It wasn't instant. It had a speed, which meant it obeyed laws, physical laws, that could be measured, studied, and understood. And if light had a speed, then everything we thought we knew about seeing about time, about the structure of the universe itself, might need to be reconsidered. But this was only the beginning. Rumor had opened a door, but he couldn't see what lay beyond it. Over the next 2 centuries, scientists would refine their measurements, making them more and more precise. And the more precisely they measured, the stranger things became. What they discovered next would lead to a crisis in physics, one that would eventually require a complete reimagining of space and time. By the late 1800s, physicists had refined their measurements of light's speed to extraordinary precision. But the more accurately they measured, the more a troubling question emerged. If light has a speed, why does it seem to ignore the basic rules of motion that govern everything else? Think about how speed normally works. It's common sense, really. Something you learned without even trying. If you're on a train moving at 60 miles per hour and you throw a ball forward at 20 miles per hour, someone standing on the ground will see the ball moving at 80 miles per hour. The speeds add up. If you throw the ball backward at 20 miles per hour, the ground observer sees it moving at 40 miles per hour. Simple arithmetic. First grade math, right? This principle, called velocity addition, was fundamental to Newtonian physics. It applied to everything cannonballs planets, sound waves, water waves. Every form of motion in the universe obeyed this straightforward rule, except, as it turned out, light. In the 19th century, scientists were convinced that light, like sound or water waves, must need some medium to travel through. Sound needs air or water to propagate. Remove the medium, and sound cannot exist. Ocean waves need water. So light, being a wave, must also need something to carry it. They called this mysterious substance the ether. The ether was imagined as an invisible, weightless substance that filled all of a space, permeating everything: the air, the vacuum between planets, the vast emptiness between stars. It had to be incredibly thin, offering no resistance to planets or comets moving through it, yet somehow rigid enough to carry light waves at enormous speeds. It was a strange concept, but it seemed necessary. And if the ether existed, then Earth's motion through it should be detectable. Earth orbits the Sun at about 18 miles per second, roughly 67,000 miles per hour. That's an enormous speed. As Earth plows through this cosmic ether, there should be a massive ether wind, blowing past us just like you feel wind when you stick your hand out of a moving car window. And this ether wind should affect the speed of light, making light travel faster when moving with the wind and slower when moving against it. This was testable, and in 1887, two meticulous scientists decided to test it. Albert Michelson was a master of precision measurement, obsessed with accuracy down to the smallest fraction. Edward Morley was a careful chemist, known for his painstaking attention to detail. Together, they designed one of the most important experiments in the history of science. Their goal was simple: detect the ether wind by measuring tiny differences in the speed of light traveling in different directions. Their device, called an interferometer, was ingeniously sensitive. It split a beam of light into two perpendicular paths, sent them bouncing off mirrors, then brought them back together. If light traveled at different speeds in different directions due to the ether wind, the two beams would fall slightly out of sync, creating a distinctive interference pattern. The device was so sensitive, it could detect differences smaller than a single wavelength of light. They set up their equipment on a massive stone slab, floating in a pool of mercury to eliminate any vibrations. They measured in different seasons at different times of day, pointing their instrument in every possible direction. If the ether existed and Earth was moving through it, they would see a clear signal light moving along Earth's direction of motion should travel at a different speed than light moving perpendicular to it. They ran the experiment hundreds of times. They checked and rechecked their calculations. They varied every parameter they could think of. And the result? Nothing. Absolutely nothing. No difference whatsoever. The speed of light was identical in every direction they measured, regardless of Earth's motion through space. The precision of their null result was staggering. They could detect changes as small as 0.001%, but the actual change was zero. This wasn't just unexpected, it was impossible. According to everything physics knew about motion, this result made no sense. It was like discovering that 1 plus 1 no longer equals 2, that the fundamental arithmetic of the universe had suddenly broken down. The scientific community was thrown into crisis. The Michelson-Morley experiment seemed to suggest that either the ether didn't exist or something deeply strange was happening with the nature of motion itself. But abandoning the ether meant abandoning the very framework for understanding how light worked, and accepting that light's speed didn't change regardless of the observer's motion meant throwing out Newton's laws of motion, which had worked flawlessly for 2 centuries. Physicists refused to accept it. They invented increasingly elaborate explanations to save the ether theory. Maybe Earth somehow drags the ether along with it, so there's no relative motion, but that contradicted other observations. Maybe objects physically contract when moving through the ether, and this contraction exactly compensates for the expected change in light speed. This idea, proposed by physicists like Fitzgerald and Lorentz, was mathematically clever, but felt like a desperate patch on a failing theory. Maybe there were local ether eddies, or the ether had different properties in different regions. Every hypothesis failed. Each new experiment only confirmed the maddening result. The speed of light was constant, always and everywhere, completely independent of the motion of either the source or the observer. It defied logic. It defied common sense. It defied everything Newton had taught. For 18 years, physics remained stuck in this deadlock. The greatest minds of the era wrestled with the problem, proposing theory after theory, each more convoluted than the last. What was needed wasn't a better version of the old ideas. What was needed was someone willing to think in a completely different way. Someone not trapped by the assumptions of classical physics. Someone unburdened by academic tradition. That person appeared in 1905, and he came from the most unlikely place imaginable, not from the universities or the great research laboratories, but from a patent office in Switzerland. Albert Einstein wasn't a distinguished professor at a prestigious university. He wasn't surrounded by laboratories full of equipment or assistants. In 1905, he was 26 years old, working as a third-class examiner at the Swiss Patent Office in Bern. He didn't even have a doctorate yet. His job was to review patent applications, drawings of new inventions, proposals for improved machines, technical documents describing incremental improvements to existing technology. It was by most measures boring work, but Einstein had something most academic physicists didn't time to think freely without the pressure to conform to established theories or please senior professors. During the day, he processed patents. At night and on weekends, he thought about light motion, space, and time. He had no laboratory, just a pen, some paper, and an extraordinary mind willing to question everything. Einstein had been obsessed with light since he was a teenager. At 16, he'd asked himself a deceptively simple question. What would I see if I could chase after a beam of light at the speed of light itself? Would I see the light wave frozen in front of me, standing still like a snapshot? It was a beautiful thought experiment, the kind that seems almost childish in its simplicity. But when Einstein tried to work through the implications using Maxwell's equations, the fundamental laws of electromagnetism, he ran into a problem. According to Maxwell, a frozen light wave, a wave standing completely still, was mathematical nonsense. It couldn't exist. Light, by its very nature, must always move at a specific speed. There was no such thing as stationary light. This contradiction gnawed at him for years. If you can't catch up to light, if light always moves at the same speed, no matter how fast you're going, then something fundamental must be wrong with our understanding of motion. But what most physicists were trying to fix the theory of light adjusting Maxwell's equations or inventing new properties for the ether. Einstein did the opposite. What if Maxwell's equations were correct, and the problem was with our understanding of space and time themselves? What if the very concepts of distance and duration, things that seemed fixed and absolute, were actually flexible? This was a radical leap. For thousands of years, space and time had been treated as the immovable stage on which events played out. Space was where things happened. Time was the universal clock, ticking forward, the same for everyone everywhere. Newton had built his entire system of physics on this foundation. But Einstein asked, what if that foundation is wrong? If the speed of light must be the same for everyone always, then the only way to make that work mathematically is if space and time themselves adjust to keep light's speed constant. This wasn't a measurement error. This wasn't an illusion or an artifact of the equipment. This was the fundamental nature of reality. Einstein built his theory on two simple principles. First, the laws of physics are the same for everyone moving at constant velocity. Whether you're sitting still on Earth or traveling smoothly on a train, the same physical laws apply. You can't tell by doing a physics experiment whether you're really moving or really at rest. There's no absolute reference frame, no privileged position in the universe. Second, the speed of light in a vacuum is the same for all observers regardless of their motion or the motion of the light source. Whether you're standing still or racing toward a light beam at half the speed of light, you will measure that beam traveling at exactly 186,282 miles per second, not 186,282 plus your speed, not 186,282 minus your speed, exactly 186,282 miles per second. Always. These principles sound simple, almost innocent, but the consequences that flowed from them were revolutionary, upending centuries of intuition about how the universe works. From these two principles, Einstein derived a series of shocking conclusions. Time dilation, time flows more slowly for objects moving at high speeds. A clock on a fast-moving spaceship ticks slower than an identical clock sitting still, not because the clock is broken, but because time itself runs at different rates depending on your motion. Length contraction objects shrink along their direction of motion. A spaceship traveling near the speed of light becomes compressed shorter from the perspective of someone watching it pass by. Mass-energy equivalence. Mass and energy are two forms of the same thing interconvertible through the equation E equals mc squared, where c is the speed of light. And finally, the cosmic speed limit. Nothing with mass can ever reach the speed of light, because doing so would require infinite energy. Einstein published these ideas in June 1905 in a paper titled On the Electrodynamics of Moving Bodies. There were no footnotes, no references to other scientists' work. He'd developed these ideas during his spare time, working them out in his head and on scraps of paper. The paper was initially ignored by most of the physics community. When people did start paying attention, the reaction was fierce debate, skepticism, even outright hostility. It took nearly a decade for Einstein's theory of special relativity to gain widespread acceptance. The ideas were too strange, too counterintuitive. Time that flows at different rates, space that contracts and expands mass, and energy as interchangeable. These violated every instinct built from a lifetime of everyday experience. But gradually, as more experiments confirmed Einstein's predictions, resistance crumbled. The evidence was undeniable. Einstein had done something extraordinary, working alone without institutional support, using nothing but pure thought. He had fundamentally rewritten our understanding of space-time and motion. He had shown that the universe was far stranger, far more flexible than anyone had imagined. And at the heart of it all was that cosmic speed limit the speed of light unchanging and absolute, woven into the very fabric of space-time itself. But these consequences sound like science fiction. Why? Why can't anything reach the speed of light? The answer lies in one of the strangest concepts in physics, the idea that as you approach light speed, your mass grows toward infinity. Imagine you have access to the most powerful spaceship ever conceived. Not something from today's technology, but a vessel with an engine so advanced it seems almost magical, capable of channeling the energy output of an entire star if needed. You climb aboard, strap yourself in and begin accelerating from rest. At first, everything behaves exactly as you'd expect. The acceleration is smooth and steady. You watch the speedometer climb 1,000 miles per hour, 10,000, 100,000. The stars outside begin to shift noticeably as you pick up speed. Your velocity keeps rising, 1%. The speed of light, 5%, 10%. The engine hums with power, and you're making excellent progress. Everything feels normal, predictable, following the laws of motion you learned in school. But then something starts to change. Subtly at first, then more obviously. As you push past 30 or 40% the speed of light, you notice the acceleration isn't as smooth anymore. The engine is working just as hard, pouring out the same tremendous energy. But your speed isn't increasing as quickly as it should. It's as if you're pushing against resistance that wasn't there before, like trying to push a car up a hill that's gradually getting steeper and steeper. You push the throttle harder. The engine responds, channeling even more energy into acceleration, but the effect is diminishing. The faster you go, the less impact each burst of energy has on your actual speed. You're climbing from 50% to 60% the speed of light, but it's taking far more energy than it took to climb from 40 to 50%, and the pattern only gets worse. Let's look at the numbers, because they reveal something profound and disturbing about the structure of reality itself. At 50% the speed of light, you need about 15% more energy than Newton's laws would predict. That's noticeable, but not catastrophic. You can work with that. At 90% the speed of light, things have gotten much worse. You need more than double the energy that classical physics says you should. The efficiency has fallen off dramatically. At 99% the speed of light, you need 7 times the energy Newton's equations predict. Your engines are screaming, consuming fuel at an enormous rate, and you've only gained another 9% of light speed. At 99.9%, adding just that extra 0.9%, you need 22 times the predicted energy. The numbers are starting to look absurd. At 99.99%, you need roughly 70 times the energy. At 99.9999%, you need 707 times the energy. Do you see the pattern? Every tiny increment closer to light speed requires exponentially more energy. The curve isn't just steep, it's becoming vertical, approaching an asymptote. And at exactly 100%, at precisely the speed of light itself, the energy requirement becomes infinite, not extremely large, not more than we could ever produce, literally infinite, an infinite amount of energy, which is not just impractical, but mathematically and physically impossible. The universe contains only a finite amount of energy. Therefore, reaching exactly 100% the speed of light is impossible for anything with mass. Not difficult, not merely a technological challenge. Impossible in the deepest, most fundamental sense of the word. But why? Why does the universe behave this way? The answer lies in the nature of space-time itself, in the deep geometric structure that Einstein revealed. Space and time aren't two separate things, as our everyday experience suggests. They're not independent dimensions that exist side by side. Instead, they're intimately woven together into a single four-dimensional fabric that physicists call space-time. When you move through space, you're not just moving through space, you're also affecting how you move through time. The two are linked in a profound way. Here's the key insight. Everything in the universe is always moving through space-time at exactly the speed of light. Always. This sounds strange at first, but think of it this way. Space-time has 4 dimensions: 3 of space, up, down, left, right, forward, backward, and 1 of time. Your total motion through this 4-dimensional space-time is constant and always equals the speed of light. When you're sitting still, not moving through space at all of your motion is directed through time. You're traveling into the future at exactly 1 second per second. That's what sitting still means. In the language of space-time, you're moving through time at the maximum possible rate with 0 motion through space. But when you start moving through space, something has to give. Your total motion through space-time is fixed at the speed of light. So if some of that motion gets redirected into spatial dimensions, less of it remains available for motion through time. Your clock starts ticking more slowly relative to someone who's not moving with you. This is time dilation, not a malfunction or an illusion, but a direct consequence of how motion works in space-time. As you move faster and faster through space, more and more of your motion gets diverted from time into space. Your watch ticks slower. Your heartbeat slows down. All physical processes in your reference frame run at a reduced rate compared to the outside world. And crucially, you're approaching a limit. At the speed of light, if you could somehow reach it, 100% of your motion would be through space and 0% through time. Time would stop completely. This is the state that photons exist in. Photons are always moving at light speed, and from their perspective, if they had one, time doesn't pass at all. A photon emitted from a distant galaxy billions of years ago experiences 0 elapsed time during its journey to your eye. For the photon emission and absorption are the same instant, but photons can do this only because they have no rest mass. They're pure energy patterns in electromagnetic fields with no mass to slow them down. For anything with mass electrons, atoms, spaceships, human beings reaching light speed would mean stopping time entirely, and that requires the infinite energy we talked about earlier. Here's another way to understand it. As you accelerate closer to light speed, the energy you're pumping into your spaceship doesn't translate into more speed. Instead, it translates into more mass. Your relativistic mass increases. The spaceship becomes harder and harder to accelerate, not because the engine is weakening, but because the ship itself is becoming more massive with every increment of speed. At light speed, your mass would become infinite, which is another way of saying it's impossible. This increasing mass isn't something you'd feel directly if you were on the ship. From your perspective inside, everything would seem normal. But from the perspective of someone watching you accelerate past them, your ship would appear to gain mass, becoming heavier and more resistant to further acceleration. The faster you go, the more energy goes into increasing your mass rather than your speed. You're pushing against a wall that grows stronger without limit. This cosmic speed limit isn't a rule imposed from outside like a law passed by some cosmic legislature. It's not that the universe has decided arbitrarily that nothing should go faster than a 282 miles per second. Rather, it's a natural consequence of the geometry of space-time itself. It's built into the structure of reality at the most fundamental level. Think about it this way. Asking, "Why can't I go faster than light?" is like asking, "Why can't I draw a square circle?" Or, "Why can't I go north of the North Pole?" These aren't rules enforced by some external authority. They're logical impossibilities, contradictions in terms. Once you understand what the words mean, what square and circle mean, what north and North Pole mean, you realize the question doesn't make sense. Similarly, once you understand what space-time and motion really are, once you grasp that they're all aspects of a unified spacetime with a particular geometric structure, you realize that going faster than light isn't something that's forbidden by a law. It's something that's internally contradictory, like asking for a number bigger than infinity. The speed of light isn't a speed limit in the usual sense. It's more like the exchange rate between space and time, the fundamental constant that defines their relationship. This is why Einstein's theory is called relativity. Not because everything is relative in some vague philosophical sense, but because the one absolute universal constant is the speed of light in vacuum. Everything else, measurements of distance, duration, simultaneity, even mass, depends on the observer's reference frame. But the speed of light is the same for everyone, everywhere, always. It's the one fixed point in a universe where almost everything else is flexible. So we've arrived at the answer to our question: nothing can go faster than the speed of light, because the speed of light isn't really about light. It's about the structure of space-time itself. It's the maximum rate at which cause and effect can propagate through the universe. It's the speed at which massless particles must travel, and the unreachable limit that particles with mass asymptotically approach, but can never reach. It's woven into the fabric of reality so deeply that asking why nothing can exceed it is like asking why reality is real. But this is only the beginning of the story. We've understood why the cosmic speed limit exists, but we haven't yet explored what happens when you try to push against it. What does reality look like when you're traveling at 90%, 99%, 99.9% the speed of light? The consequences are far stranger than anything we've discussed so far, because when you approach the cosmic speed limit, reality itself begins to warp in ways that defy everyday intuition. Time stretches, space compresses, and the universe transforms into something almost unrecognizable. Let me tell you a story about two brothers, identical twins, born on the same day genetically, the same aging at the same rate throughout their childhood. When they turn 30, one of them, let's call him Alex, becomes an astronaut and boards a spacecraft capable of traveling at 99.5% the speed of light. His mission: reach a star system 20 light years away and return home. His twin brother Marcus stays on Earth living an ordinary life. From Marcus's perspective on Earth, the journey is straightforward. Alex's ship travels 20 light years at nearly light speed, taking just over 20 years to get there. Then another 20 plus years to return. Total trip time about 40 years. When Alex's ship finally lands back on Earth, Marcus rushes to greet his brother. He's now 70 years old, his hair gray, his face lined with the creases of 4 decades. But when Alex steps out of the spacecraft, Marcus gasps. His twin brother looks barely older than the day he left. Alex has aged only about 4 years. He's 34 years old, biologically, genuinely 34. This isn't an illusion created by suspended animation or cryogenic freezing. Alex was awake and alive for the entire journey. He ate meals, read books, exercised thought about home. But for him, the journey took 4 years. For Marcus, it took 40. How is this possible? The answer lies in one of the most bizarre consequences of approaching light speed time dilation. Time itself flows at different rates depending on how fast you're moving. This isn't a metaphor or a trick of perception. Time literally, physically passes more slowly for objects moving at high speeds. The mathematics is surprisingly simple, governed by what's called the Lorentz factor. At 50%, the speed of light time passes at 87% its normal rate. You age 87 seconds for every 100 seconds that pass for someone at rest. The effect is noticeable, but not dramatic. At 90%, light speed time slows to 44%, less than half the normal rate. You experience 44 seconds, while someone stationary experiences a 100. At 99%, the speed of light time crawls at just 14% normal speed. At 99.9%, it's down to 4.5%. At 99.99%, time flows at only 1.4% its usual rate. The closer you get to light speed, the more extreme the effect becomes, approaching a limit where time nearly stops altogether. This has been confirmed by countless experiments, starting with one of the most elegant tests in the history of physics. In 1971, physicists Joseph Haefel and Richard Keating took 4 cesium atomic clocks, among the most precise timepieces ever built, and flew them around the world on commercial airliners. They flew some clocks eastward and others westward, then compared them to identical clocks that had remained on the ground at the U.S. Naval Observatory. When they analyzed the results, they found exactly what Einstein had predicted. The flying clocks had aged less than the stationary clocks. The difference was tiny, only a few hundred nanoseconds, but it was real measurable and precisely matched the predictions of relativity. Time dilation isn't theoretical speculation. It's a fact you can measure with a good clock and an airplane ticket. But perhaps the most dramatic evidence comes from particles called muons, created when cosmic rays slam into the upper atmosphere. Muons are unstable. They have a built-in expiration date of about 2.2 microseconds. After that brief moment, they decay into other particles. They are born at altitudes of around 10 to 12 miles up, traveling at nearly the speed of light downward toward Earth's surface. Here's the problem. Even moving at nearly light speed, a muon should only travel about 2,000 feet before its 2.2 microseconds are up and it decays. It should never make it to the ground. And yet we detect muons at sea level all the time. Muon detectors register them constantly, a steady rain of particles that, according to classical physics, shouldn't exist by the time they reach us. The explanation is time dilation. From Earth's perspective, the muons are moving so fast that their internal clocks run slow. Their 2.2 microsecond lifespan gets stretched out to dozens of microseconds, enough time to complete the journey to the surface. We see them live longer because time itself is passing more slowly for them. And this isn't just some exotic particle physics phenomenon. It happens every single day in particle accelerators around the world. The Large Hadron Collider, the world's most powerful particle accelerator, routinely accelerates protons to 99.99991% the speed of light. At that speed, the protons' clocks run about 7,000 times slower than ours. Physicists must account for time dilation when calculating the protons' trajectories and collision points. If they ignored relativity, the entire machine would fail. The collisions wouldn't happen where predicted. The experiments wouldn't work. The philosophical implications are staggering. Time doesn't flow at an absolute rate. There's no universal cosmic clock ticking away at the same pace everywhere. Each object, each person, has their own personal timeline, their own rate of aging determined by how they move through space. Two people moving at different velocities are literally experiencing time at different rates. At the same time becomes a relative concept dependent on your reference frame. This opens up a form of one-way time travel to the future. If you could board a spacecraft and accelerate to near light speed, you could travel decades, centuries, even millennia into Earth's future, while aging only a few years yourself. You'd be moving forward through time faster than everyone else, or more accurately, everyone else would be moving forward faster than you, while from your perspective, everything would seem normal. This isn't science fiction. It's real physics. The only thing preventing us from doing it is technology. We don't yet have engines capable of reaching such speeds, but the physics is sound tested thousands of times. If we built the ship, time dilation would happen exactly as Einstein predicted. There's a price, though. This time travel is one way only. You can skip forward into the future, but you can never go back. The years you've leaped over are gone forever. Everyone you knew will have aged or died. The world will have moved on without you. Time dilation is a door that only opens in one direction, but time dilation is only half the story, and perhaps not even the strangest half. Let's return to those muons for a moment, but look at the situation from a different perspective, the muon's own point of view. From Earth's frame of reference, we explained their survival by saying, time dilation extends their lifespan. They live longer so they can complete the journey. But here's the puzzle. From the muon's perspective, there is no time dilation. The muon experiences time normally. Its internal clock hasn't slowed down at all. From its point of view, it lives exactly 2.2 microseconds, just as it should. So how does it reach the ground before decaying? The answer is length contraction. From the muon's perspective, the distance to Earth's surface isn't 10 miles. It's compressed, squeezed down to about 2,000 feet. The journey is shorter, so even with its brief lifespan, it completes the trip. Both explanations are correct. From Earth's view, the muon lives longer. From the muon's view, the distance is shorter. Two different descriptions of the same reality, both equally valid. This is length contraction, and it follows the same mathematics as time dilation. At 50%, the speed of light lengths contract to 87% of their rest length. At 90%, they shrink to 44%. At 99%, down to 14%. At 99.9%, a mere 4.5% remains. Objects become compressed along their direction of motion, squeezed like an accordion. Though only in that one direction, they don't shrink vertically, or side to side, only front to back. Let's make this concrete with an example of interstellar travel. Proxima Centauri is the nearest star to our Sun, sitting about 4.24 light years away. If you traveled there at 99.9% the speed of light, here's what would happen from two different perspectives. From Earth's perspective, the distance is 4.24 light years. Your ship is traveling at 99.9% light speed, so the journey takes about 4.27 years. People on Earth Watch you go wait 427 years and see you arrive. They age 427 years during your journey. Straightforward. But from your perspective, aboard the ship, something strange happens. The distance to Proxima Centauri isn't 424 light years anymore. It's contracted down to about 0.19 light years, roughly 1.8 light months. Your journey from your point of view takes only about 2.3 months. You age just 2.3 months, while Earth ages 427 years. Both perspectives are correct. The discrepancy isn't an error, it's the nature of space-time itself. This leads to one of the most famous thought experiments in relativity, the pole barn paradox, sometimes called the ladder paradox. Imagine a runner carrying a 20-meter pole sprinting toward a 10-meter barn. Obviously, when both are at rest, the pole is twice as long as the barn. It can't fit inside, but suppose the runner accelerates to 86.6% the speed of light. From the barn's perspective, the moving pole undergoes length contraction, shrinking to exactly 10 meters. It fits perfectly inside the barn. You could, in principle, close both doors simultaneously, trapping the pole completely within the barn's walls. But wait, from the runner's perspective, the runner and pole are stationary. It's the barn that's moving toward them at 86.6% light speed. So, from the runner's view, the barn contracts to 5 meters, while the pole remains 20 meters long. There's no way the pole fits inside. The pole is 4 times longer than the barn. So, what actually happens? Can both doors close with the pole inside or not? This seems like a genuine paradox, a logical contradiction, but the resolution reveals something profound about the nature of reality. The key is the relativity of simultaneity. Closing both doors at the same time is true for the barn observer, but not for the runner. Events that are simultaneous in one reference frame aren't simultaneous in another. From the barn's perspective, yes, both doors close at the same instant, briefly containing the pole. But from the runner's perspective, the front door closes first, then opens again before the back door closes. The pole is never actually trapped. There's always an opening. Both observers see consistent, non-contradictory sequences of events. They just disagree about the timing and ordering. There's no absolute same time that everyone agrees on. Simultaneity itself is relative dependent on motion. This has profound consequences for how we understand space. Space isn't a rigid, unchanging stage where events play out. It's a flexible entity that expands and contracts depending on relative motion. Distance is not absolute. How far apart two objects are depends on how fast you're moving relative to them. Size isn't absolute either. How big something is depends on your reference frame. The only thing that's absolute that all observers agree on is the combined structure of space-time, the four-dimensional fabric that blends space and time together. This also explains why there can be no perfectly rigid objects in the universe. Imagine you had a perfectly rigid pole and pushed one end. If the pole were truly rigid, the other end would have to move instantaneously. Otherwise, the pole would compress slightly, meaning it's not perfectly rigid. But instantaneous transmission of force violates the cosmic speed limit. Information can't travel faster than light. The resolution: there are no perfectly rigid materials. When you push one end of any object, what actually happens is that a compression wave travels through the material at the speed of sound in that substance. The atoms at one end jostle their neighbors, which jostle their neighbors, and the disturbance propagates through the object at some finite speed, and that speed in any material is always less than the speed of light. Every interaction, every force, every cause and effect must respect the cosmic speed limit. So, time slows down and space compresses. But there's a third consequence of approaching light speed 1 that's perhaps even harder to wrap your mind around. When you accelerate toward light speed, you don't just move faster, you become heavier, your mass growing without limit. There's a massive circular tunnel buried beneath the border between France and Switzerland, 27 kilometers around, lined with thousands of superconducting magnets, cooled to nearly absolute zero. This is the Large Hadron Collider, the most powerful particle accelerator ever built, and inside it, protons race around the ring at 99.991% the speed of light. That's an absurdly precise number, 11,999,991 parts out of 12 million. The LHC consumes about 200 megawatts of electricity when running at full power, enough to supply a small city. All that energy goes into pushing protons just a tiny bit faster, squeezing out that last fraction of a percent toward light speed. And yet, despite this enormous energy expenditure, despite magnets powerful enough to rip the iron from your blood, if you got too close, the LHC cannot push those protons that final 0.09% to reach exactly the speed of light. Why? Because at 99.9999991% light speed, each proton has a relativistic mass about 7,000 times greater than its rest mass. Those protons aren't just moving fast, they've become thousands of times heavier, thousands of times harder to accelerate further. Every additional increment of speed requires exponentially more energy, because you're not just fighting inertia anymore, you're fighting the fundamental structure of space-time itself. This is relativistic mass increase, the third strange consequence of approaching light speed. Every object has what's called a rest mass, the mass it has when sitting completely still. This is the mass you'd measure if you put the object on a scale. But when an object starts moving, it gains what we call relativistic mass. This isn't because the object is accumulating more atoms, or because matter is somehow being added to it. Rather, the energy of motion itself manifests as additional mass. The faster you go, the more of your kinetic energy converts into mass rather than speed. It's as if the universe is saying, you want to go faster, fine, but you're going to get heavier in the process, and that's going to make going even faster progressively more difficult. The numbers tell the story. At 50% the speed of light, your mass increases by about 15%. You're noticeably heavier, but not catastrophically so. At 90% light speed, your mass has more than doubled. You're 2.3 times heavier than at rest. At 99%, you're 7 times heavier. At 99.9%, you're 22 times your rest mass. At 99.99%, you've ballooned to 70 times your original mass. Do you see where this is going? At exactly 100%, at precisely the speed of light, your mass would become infinite, not extremely large or bigger than a galaxy, literally infinite. And an object with infinite mass cannot exist in our universe. It's not just impractical, it's a logical impossibility. a mathematical singularity that nature forbids. This mass-energy relationship is encoded in the most famous equation in all of physics, E equals mc squared. Energy equals mass times the speed of light squared. This simple equation reveals something profound. Energy and mass are not different things. They're two forms of the same fundamental quantity. You can convert mass into energy and energy into mass. They're interchangeable like dollars and euros, with the speed of light squared serving as the exchange rate. And what an exchange rate it is. The speed of light is about 300 million meters per second. Square that, and you get 90 quadrillion meters squared per second, squared 9, followed by 16 zeros. That's an enormous number, which means a tiny amount of mass contains a staggering amount of energy. Consider the sun. Every single second, the sun converts about 4 million tons of mass into pure energy through nuclear fusion. Deep in its core, hydrogen atoms are being crushed together under enormous pressure and temperature, fusing into helium. Here's the key: 4 hydrogen nuclei weigh slightly more than 1 helium nucleus. That tiny difference in mass, less than 1%, gets converted into energy according to Einstein's equation. That's where sunlight comes from. That's what keeps the sun burning. That's why you're alive. The same principle powers or destroys through nuclear weapons. The atomic bomb dropped on Hiroshima released energy equivalent to about 15,000 tons of TNT, and the amount of matter that was actually converted from mass into energy, about 1 gram. 1 single gram of matter converted into pure energy leveled a city. That's the terrifying power locked inside E equals mc squared. Nuclear power plants exploit this equation in a controlled way, using nuclear fission to convert tiny amounts of mass into electricity. Every chemical reaction, burning wood, digesting food, rusting iron, involves minuscule conversions between mass and energy. The products of the reaction weigh slightly less than the reactants, and that mass difference becomes heat or light. Your own body is performing trillions of these tiny conversions every second. As it metabolizes, food sends electrical signals through neurons, moves muscles. You are a living demonstration of mass energy equivalence. This brings us back to why photons, particles of light, can travel at light speed while everything else cannot. Photons have 0 rest mass, not almost 0 or really tiny, exactly 0. Because they have no rest mass, they don't experience the relativistic mass increase that plagues particles with mass. They naturally, inevitably move at the maximum speed allowed by the universe. And because they have no mass, they can never slow down or stop. A photon is always in motion at light speed from the moment it's created until the moment it's absorbed. This is the fundamental asymmetry in nature. Massless particles must always move at light speed. Particles with mass must always move slower than light speed. There's no middle ground, no way to transition from one state to the other. The cosmic speed limit divides the universe into 2 categories: things that have mass and can never reach light speed, and things without mass that can never travel at any other speed. So now we've seen 3 interconnected consequences of approaching light speed. Time dilation slows your clock. Length contraction compresses the space in front of you. and relativistic mass increase makes you heavier, harder to accelerate, asymptotically approaching infinite mass as you approach light speed. These aren't separate phenomena, they're different manifestations of the same underlying reality, different ways that space time responds to motion. And all three have been confirmed by thousands upon thousands of experiments. Time dilation is verified every time a GPS satellite calculates your position. Length contraction explains why moons reach the ground. Relativistic mass increase is something particle physicists deal with every single day in accelerators around the world. This isn't speculation or theoretical fantasy. It's documented, measured, verified reality. But here's something that might be bothering you. If all this is true, why don't we see it in everyday life? You've never noticed time slowing down when you drive fast. You've never seen a race car get shorter as it speeds past. You've never felt yourself getting heavier when you run. The answer is simple: because we're so incredibly slow. The fastest car in the world moves at about 300 miles per hour. That sounds fast, but it's only 0.04% the speed of light. At that speed, the relativistic effects exist. They're real, but they're vanishingly tiny, far too small for our senses or even our instruments to detect. You'd need to be moving at least 10% the speed of light before these effects become noticeable, and closer to 50% before they become dramatic. We live in the slow motion universe, crawling along at speeds where space-time barely flexes at all. And because our everyday experience is limited to these glacial velocities, relativity seems bizarre and counterintuitive. But that's only because we've never experienced the high-speed realm where its effects become obvious. But there's evidence all around us, hidden in plain sight in the technology, in your pocket, in the chemistry of the metals you touch, in the very light entering your eyes right now. Right now, there's probably a device in your pocket or bag that depends entirely on Einstein's theory of relativity to function, without accounting for the strange effects we've been discussing: time dilation, the warping of space-time. This device would be completely useless, accumulating errors so rapidly that it would fail within minutes. That device is your smartphone, and the technology is GPS. GPS satellites orbit Earth at an altitude of about 12 to 400 miles, traveling at roughly 8,700 miles per hour. There are currently 31 of these satellites, forming a network around the planet, each one carrying an atomic clock accurate to within billionths of a second. When you open your Maps app and ask for directions, your phone receives signals from at least 4 of these satellites. By comparing the timing of those signals, your phone can calculate your position to within a few feet. But here's where relativity becomes essential. Those satellites are moving fast and orbiting high above Earth's surface, which means they experience 2 competing relativistic effects. First, because they're moving at 8,700 miles per hour, relative to the ground, their clocks run slower due to time dilation. This velocity effect causes their clocks to lose about 7 microseconds per day, 7 millionths of a second. But there's a second effect, one we haven't discussed yet, coming from Einstein's general theory of relativity. The satellites are in a weaker gravitational field than we are on the surface. Gravity itself warps space-time. The stronger the gravity, the slower time flows. up where the satellites orbit, gravity is weaker, so time actually runs faster. This gravitational effect causes their clocks to gain about 45 microseconds per day. These two effects work in opposite directions. The velocity slows the clocks down by 7 microseconds, but the weaker gravity speeds them up by 45 microseconds. The net result: the satellite clocks run fast by about 38 microseconds every single day compared to clocks on the ground. 38 microseconds doesn't sound like much, but light travels about 300 meters in a single microsecond. So, if you didn't correct for this relativistic time difference, the position calculations would drift by about 38 microseconds times 300 meters, roughly 11 kilometers per microsecond, accumulating to errors of about 10 kilometers per day. After just one day, your GPS would think you're 6 miles away from where you actually are. Turn-by-turn navigation would be impossible. Google Maps would be useless. Uber drivers would never find you. In reality, engineers who designed the GPS system had to program Einstein's equations directly into the satellite software. The satellites continuously adjust their clock rates to compensate for relativistic effects. Every time you check your location, your phone is using the theory of relativity to tell you where you are. You might not realize it, but you're using Einstein's insights about the nature of space-time dozens of times a day. This isn't the only everyday technology that relies on relativity. Consider PET scans, positron emission tomography, a medical imaging technique used to detect cancer, study brain function, and diagnose heart disease. The positron in the name refers to antimatter, specifically the antimatter counterpart of the electron. Here's how it works. Doctors inject a patient with a substance containing radioactive atoms that emit positrons. When a positron encounters a regular electron in the patient's body, the two particles annihilate each other, completely converting their entire mass into pure energy in the form of two gamma rays, shooting off in opposite directions. This is E equals mc squared in action, demonstrated inside living tissue. Detectors surrounding the patient pick up these gamma rays. By tracking where the annihilations happen, doctors can create detailed three-dimensional images of metabolic activity inside the body. Cancer cells, which consume energy, rapidly show up as bright spots. Brain regions that are active during certain thoughts light up. The technique is so powerful and precise that it's become a standard tool in modern medicine. But without Einstein's equation, without the understanding that mass and energy are interconvertible, PT scans wouldn't exist. The technology is a direct practical application of the most famous equation in physics, saving lives every day. Then there's something you might have noticed, but never thought to question. Why is gold yellow? Most metals, silver, aluminum, steel, platinum, are silver white or gray. But gold has a distinctive warm yellow color. Why, the answer lies in relativity. Gold has 79 protons in its nucleus, which means a strong positive charge pulling on the electrons orbiting around it. The innermost electrons, especially the ones in the so-called RS orbital closest to the nucleus, are moving at a significant fraction of the speed of light, fast enough that relativistic effects become important. These electrons experience relativistic mass increase, making them heavier and harder to accelerate. This changes their orbital energies in subtle but measurable ways. The energy levels shift just enough that gold absorbs blue light and reflects yellow light. That's why gold looks gold. The characteristic color of gold is a direct consequence of relativity affecting the behavior of electrons moving at relativistic speeds. Silver, by contrast, has fewer protons, only 47, so the pull on its electrons is weaker. They move more slowly. Relativistic effects are minimal, and the energy levels remain such that silver reflects all visible colors, roughly equally appearing silver-white. The difference between gold's warm yellow and silver's cool white is literally the difference between electrons moving fast enough for relativity to matter and electrons moving slow enough that it doesn't. Relativity even explains something as fundamental as magnetism. You might have learned that electricity and magnetism are two separate forces, but that's not quite right. They're actually two perspectives on the same underlying phenomenon, electromagnetism. What looks like a magnetic force from one reference frame looks like an electric force from another. Consider a wire carrying an electric current. From your perspective, standing next to the wire, you measure an electric current, electrons flowing through the conductor. But those moving electrons also create a magnetic field around the wire, which can attract or repel a magnet placed nearby. Why does motion of electric charges create magnetism? The answer involves length contraction. The moving electrons are slightly length contracted compared to the stationary positive charges in the wire's atomic nuclei. This creates a tiny imbalance in the charge density, and that imbalance manifests as what we perceive as a magnetic force. Magnetism is essentially a relativistic side effect of electricity. What happens when you view electric charges from a moving reference frame? The magnetic force exists because space and time are woven together, and motion through space affects the distribution of charge. But perhaps the most dramatic evidence for relativity comes from cosmic rays, high-energy particles that constantly rain down on Earth from space. Most cosmic rays are protons, or atomic nuclei accelerated to incredible speeds by violent events like supernova explosions or the magnetic fields around black holes. In October 1991, a cosmic ray detector in Utah registered something extraordinary. A single proton slammed into the atmosphere with an energy of about 50 joules, the energy of a baseball thrown at 100 miles per hour, compressed into a single subatomic particle. Physicists nicknamed it the "Oh my God" particle. Its speed was about 99.990 the speed of light. That's 23 nines after the decimal point. Think about what that means. This proton was traveling so close to light speed that from its perspective, the entire 93 million mile distance between Earth and the Sun would be compressed down to less than 50 feet. Time dilation would be so extreme that the proton's experience of its journey through the galaxy might last only a few seconds, even if that journey took thousands of years from our perspective. And yet, despite carrying energy 1,000,000 times greater than anything the Large Hadron Collider can produce, despite moving at a speed so close to light that it's hard to even write the number, that proton still wasn't traveling at 100% light speed. It was still in the realm of less than, still constrained by the cosmic speed limit. Nature can create conditions far more extreme than anything we can produce in our laboratories, and still always the speed of light remains inviolate. These cosmic rays hit Earth's atmosphere constantly, about 1 per square centimeter per second. Most have far less energy than the oh my god particle, but many still travel at 99.9% light speed or faster. Every one of them is a natural particle. Accelerator, a demonstration of relativity in action raining down on your head right now. The evidence is everywhere. It's in the GPS guiding your car. It's in the PET scan that can detect disease. It's in the color of the gold ring on someone's finger. It's in the magnets holding notes to your refrigerator. It's in the cosmic rays striking the atmosphere above you. Relativity isn't some abstract theory confined to textbooks and blackboards. It's woven into the fabric of reality, affecting everything from the smallest scales to the largest, from the slowest motions to the fastest. Einstein's theory isn't speculation or hypothesis anymore. It's been tested thousands upon thousands of times in countless experiments across more than a century. Every single test has confirmed it. Every prediction has come true. Time dilation, length contraction mass increase, the equivalence of mass and energy, all of it has been measured, verified, and incorporated into working technology. This is as close to certainty as science ever gets. The speed of light is the cosmic speed limit, not because of some arbitrary rule, but because that's how space-time is structured. At the deepest level, nothing with mass can reach it. Nothing with mass can exceed it. But what about the loopholes? What about wormholes, warp drives, quantum entanglement? All those science fiction concepts that seem to offer ways around the speed limit. Are any of them real? Science fiction has given us warp drives, hyperspace jumps, wormholes that let you step across the galaxy in an instant. These ideas are so embedded in our cultural imagination that it's tempting to think surely there must be some way around the cosmic speed limit, some clever trick, some exotic physics that lets us circumvent Einstein's constraints. After all, the equations of relativity are just mathematics, right? Maybe there's a loophole hidden in those equations. Here's the surprising thing. There are loopholes, or rather, there are solutions to Einstein's equations that seem to allow faster than light travel or communication. But every single one of them comes with a fatal flaw, something that makes them either impossible to create, impossible to use, or paradoxical in ways that threaten the logical consistency of the universe itself. Let's start with wormholes. In 1935, Einstein and his colleague Nathan Rosen discovered something curious in the mathematics of general relativity. The equations allow for what they called bridges, connections between two distant points in space-time. Imagine space-time as a sheet of paper. Normally, to get from point A to point B, you'd have to travel across the paper's surface. But what if you could fold the paper so that the 2 points touch, then punch a hole through? You'd create a shortcut, a tunnel connecting distant regions of space. This is a wormhole, technically called an Einstein-Rosen bridge. Crucially, traveling through a wormhole wouldn't require moving faster than light locally. You'd be moving at normal speeds through a shortcut in space-time itself. It's not about going fast, it's about taking a different route. But here's where the problems begin. For a wormhole to remain open and stable enough for anything to pass through, you'd need something called exotic matter. Matter with negative energy density. This isn't antimatter, which has positive energy. This is something far stranger, matter that has less than zero energy, that pushes instead of pulls, that violates every intuition about how mass and energy behave. We've never observed exotic matter in nature. We have no idea how to create it. It may not even be possible. It might violate fundamental conservation laws. And even if you somehow gathered enough exotic matter to create a traversable wormhole, the structure would be incredibly unstable. Any attempt to send something through would likely cause the wormhole to collapse faster than light could cross it. You'd be crushed or torn apart before you made it through. Worse, wormholes that connect different points in space can also connect different points in time. A stable, traversable wormhole could become a time machine, allowing you to travel into your own past. This creates causality, paradoxes. You could go back and prevent yourself from entering the wormhole in the first place. You could create contradictions that have no logical resolution. Stephen Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics have built-in safeguards preventing the creation of time machines. Every theoretical method we've found for building one seems to self-destruct or require impossible conditions. It's as if the universe has an immune system against paradoxes, automatically shutting down any possibility that would lead to logical contradiction. Then there's the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. This is the closest thing physics has to a theoretical warp drive. The idea is elegant. Instead of pushing your spaceship faster and faster, you manipulate space-time itself. You contract space in front of the ship and expand space behind it, creating a warp bubble that carries the ship along. The ship itself isn't moving through space. Space is moving around the ship. From the perspective of someone far away, watching you travel from Earth to Alpha Centauri, your warp bubble might cross the distance faster than light, but locally inside the bubble, you're not moving at all. You're sitting still while space-time slides past you. In principle, this doesn't violate relativity because you're not actually moving through space faster than light. You're standing still while space moves. But the Alcubierre drive has devastating problems of its own. First, the energy requirements are absurd. Initial calculations suggested you'd need negative energy equivalent to the mass of Jupiter. Later refinements reduced this to only several tons of exotic matter, which still doesn't exist and may be impossible to create. Second, once you create a warp bubble, you can't control it. You'd be causally disconnected from the front edge of the bubble. You couldn't send signals forward to turn it off or steer it, because those signals can't travel faster than light. You'd be trapped inside, unable to start or stop the drive. Third, and most fundamentally, the Alcubierre drive creates causality violations. By warping space-time in this way, you could construct closed time-like curves paths through space-time that loop back to your own past. This means you could use the drive to send signals backward in time, creating grandfather paradoxes and logical contradictions. The universe, it seems, doesn't allow this. What about tachyons, hypothetical particles that always travel faster than light? The mathematics of relativity doesn't actually forbid particles that move faster than light. As long as they always move faster than light, they can't slow down to light speed just as we can't accelerate up to it. They'd exist in a mirror realm on the other side of the speed barrier, but tachyons would have bizarre, nonsensical properties. They'd have imaginary mass involving the square root of -1, a purely mathematical construct with no physical meaning. They'd speed up when they lose energy and slow down when they gain energy, the opposite of everything else in the universe. And most problematically, they could be used to send information into the past. Here's why. Due to the relativity of simultaneity, an event that looks like sending a tachyon forward in time in one reference frame looks like receiving a tachyon from the future in another reference frame. You could use this to construct a tachyon telephone that calls your own past, telling yourself not to make the call. Paradox again. Despite decades of searching, no experiment has ever detected a tachyon. Most physicists believe they simply don't exist. The universe seems to forbid them, not through some explicit rule, but because allowing them would break causality, and causality appears to be non-negotiable. What about quantum entanglement? You might have heard that when two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance and was deeply troubled by it. Doesn't this violate the speed limit? The answer is subtle. Yes, the correlation between entangled particles is instantaneous. If you measure one particle and find it spinning up, you instantly know the other is spinning down, even if it's on the other side of the galaxy. But, and this is crucial, you can't use this correlation to send information faster than light. The measurement results are random. You can't control what you'll find when you measure your particle. Only when you compare notes with the person measuring the other particle through normal, slower than light communication do you discover the correlation. It's like having two magic coins that always land on opposite sides. The correlation is real and instantaneous, but you can't use it to send a message. You can't make your coin come up heads, so you can't encode information. Quantum entanglement preserves the correlation between particles, but not in a way that allows faster than light signaling. The cosmic speed limit remains intact. Then there's the expansion of space itself. Distant galaxies are receding from us faster than the speed of light due to the expansion of the universe. Galaxies sufficiently far away are moving away at superluminal speeds. Doesn't this violate relativity? No, because the galaxies aren't moving through space faster than light. Space itself is expanding between us and them. Imagine dots drawn on the surface of a balloon. As you inflate the balloon, the dots move apart, but they're not moving across the balloon's surface. The surface itself is stretching. The speed limit applies to motion through space, not to the expansion of space itself. This distinction is important. The cosmic speed limit governs how fast information and causal influence can propagate. It prevents you from sending a signal faster than light, but space can expand at any rate because the expansion doesn't carry information or allow causal influence to propagate faster than light. Do you see the pattern? Every apparent loophole comes with a fatal flaw. Wormholes require impossible exotic matter and create time travel paradoxes. Warp drives need unattainable energy and violate causality. Tachyons have never been detected and would break logical consistency. quantum entanglement can't transmit information. Space expansion doesn't allow faster than light signaling. The universe seems designed, or more accurately structured, to protect the cosmic speed limit, not because there's a law prohibiting faster than light travel, but because allowing it would create logical contradictions. It would permit effects to precede causes, allow messages to your own past, enable paradoxes that have no resolution. The speed of light isn't a barrier to be overcome. It's the foundation of causality, the scaffolding that keeps the universe logically coherent. It ensures that cause always precedes effect, that the future remains open rather than predetermined, that time has a direction and meaning. You might find this disappointing. It means no Star Trek warp drives no instant travel to distant stars, no galactic empires connected by faster than light communication. But there's also something profound in it. The cosmic speed limit isn't arbitrary. It's necessary for reality to make sense, for the universe to be comprehensible and consistent. Every loophole we found turns out to be a dead end or a disaster. Every clever trick for circumventing the speed limit either requires impossible conditions or creates paradoxes. The universe has, in effect, an immune system against contradictions, automatically preventing anything that would let you send messages to your own past or violate causality. This isn't just about physics or technology. It's about the logical structure of reality itself. The speed of light defines what before and after mean. It determines which events can influence each other and which cannot. It creates the flow of time from past to future, the separation between cause and effect. But this raises deeper questions. Questions not just about physics, but about existence, free will, and the very meaning of time itself. You probably think of past, present, and future as three distinct regions of time cleanly separated from each other. The past is what already happened. The future is what hasn't happened yet. And the present, right now, this very moment, is the razor-thin boundary between them, the same now, experienced by everyone, everywhere in the universe. But that's not how reality works. The structure is far more complex, far stranger than our everyday intuition suggests. And at the heart of this complexity is the cosmic speed limit. The speed of light doesn't just limit how fast things can move, it defines the very structure of time, creating the boundaries between past, present, and future. Without it, the concepts of before and after would collapse into meaninglessness. To understand this, we need to talk about light cones. Every event in space-time, you, reading this sentence right now, a supernova exploding in a distant galaxy, a photon being emitted from an atom, sits at the center of two cone-shaped regions that extend through space-time. First, there's your past light cone. This contains every event that could have possibly influenced you at this moment. It includes everything from which light or any other signal could have reached you, traveling at or below the speed of light. The cone expands backward in time at exactly the slope determined by the speed of light. Everything inside this cone is part of your causal past events that could have affected you, that you could know about, that could have shaped who you are right now. Second, there's your future light cone. This contains every event you could possibly influence from this moment forward. It includes everywhere a signal from you could reach, traveling at or below light speed. The cone expands forward in time again At the slope of light speed, everything inside this cone is part of your causal future. Events you could affect, places you could reach, people you could communicate with. But here's what's strange. Most of space-time lies outside both cones. There's a vast region called elsewhere events that are neither in your past nor in your future. These events cannot interact with you causally at this moment. A signal from them hasn't had time to reach you. A signal from you hasn't had time to reach them. You are causally disconnected. And here's the truly bizarre part. Events in this elsewhere region don't have a definite time ordering. For one observer, event A might happen before event B. For another observer, moving at a different velocity, event B happens before event A. Both perspectives are equally valid. There's no absolute answer to which happened first. The time ordering depends on who's watching. This is the relativity of simultaneity again, but seen in its full philosophical implications. Two events that are simultaneous for you, happening at the same time, from your perspective, are not simultaneous for someone moving relative to you. Observer B, traveling at high speed, sees event 1 happen before event 2. Observer C, traveling in a different direction, sees event 2 happen before event 1. All three of you are correct. There is no universal right answer about which came first. This means there is no universal now. There is no cosmic present moment that everyone agrees on. The present isn't a universal slice through time that separates past from future for everyone everywhere. Instead, each observer has their own definition of now, their own slice through space-time, and these slices tilt at different angles depending on the observer's motion. The philosophical implications are staggering. Past and future aren't cleanly separated. The boundary between them, what we call the present, is defined by the speed of light. It's the moment of becoming where the indeterminate future crystallizes into the fixed past. But this moment isn't universal. It's personal, local, dependent on your motion through space. Now, imagine a universe without a cosmic speed limit, a universe where influences could propagate instantaneously across any distance. In such a universe, there would be no light cones, no causal structure, no separation between past and future. Everything would affect everything else simultaneously. Your decisions right now would be instantly influenced by events happening on the other side of the galaxy, in other galaxies, everywhere all at once. There would be no such thing as local causation. You couldn't point to a specific cause for a specific effect because everything would be entangled with everything else in an instantaneous web of mutual influence. The concept of before and after would become meaningless. There would be no arrow of time, no clear direction from cause to effect. Time itself would collapse into chaos. This is why the cosmic speed limit is so fundamental. It's not just about motion, it's about causality. The speed of light ensures that causes always precede their effects. It creates causal distance, temporal separation, a clear ordering of events. It prevents the grandfather, paradox, and every other time travel contradiction. It gives time a direction, a flow from past to future, and makes the universe logically consistent. Without the cosmic speed limit, cause and effect would become hopelessly tangled. Effects could precede causes. You could influence your own past. Paradoxes would proliferate without resolution. The universe would be fundamentally illogical, unable to maintain any coherent, narrative of events. But with the speed limit in place, causality is protected. Information can only flow at finite speed, which means there's always a clear distinction between what came before and what came after. Events have a definite causal order within their light cones. The universe maintains logical consistency. Reality makes sense. Time has an arrow, a direction pointing from past to future, precisely because the speed of light is finite. The cosmic speed limit doesn't just constrain motion, it creates the very structure of time itself. But this raises an even deeper question. If the speed of light protects causality and gives time its structure, does it also create the conditions for something we humans value, most free will? Here's one of the oldest puzzles in philosophy. How can free will exist in a physical universe? Free will suggests the ability to make genuine choices, decisions that aren't entirely determined by what came before. But physics tells us the universe operates according to laws, precise deterministic equations that govern how matter and energy behave. If everything follows these laws, if every effect has a cause stretching back to the Big Bang, where is there room for choice? The answer might lie in an unexpected place, the cosmic speed limit. Consider what would happen in a universe without any speed limit, where all influences propagate instantaneously. In such a universe, every particle would be in constant immediate communication with every other particle. The state of your brain right now would be instantly affected by the position of every star, every galaxy, every atom in the entire cosmos. You wouldn't be a local system making local decisions. You'd be a node in an instantaneous universal network, your every thought shaped simultaneously by everything everywhere. In this hypothetical universe, there's no separation between you and the rest of the universe. There's no protective bubble where your brain can process information and make decisions according to its own internal logic before being influenced by distant events. Everything influences everything else at the same instant, creating a single unified system with no autonomous parts. Your decisions, if you could even call them that, would be the inevitable product of the entire state of the universe at every moment. There would be no space for anything resembling free will, no room for genuine novelty or unpredictability. The future would be rigidly determined by the present, which was rigidly determined by the past in an unbroken chain stretching back to the beginning of time. But our universe isn't like that. The speed of light is finite, and this creates something crucial: causal distance. When you make a decision, your brain has a few milliseconds, sometimes longer, to process information locally before influences from distant events can reach you. Light from the nearest star takes 4 years to arrive. Light from distant galaxies takes millions or billions of years. Within the protective bubble of your light cone, your brain can operate according to its own internal dynamics, its own evolved algorithms, its own patterns of neural activity. This doesn't mean your decisions are uncaused or random. They're still the product of physical processes in your brain, shaped by your genes, your memories, your environment. But crucially, they're the product of local processes, not the instantaneous sum of everything in the universe. The finite speed of light creates a kind of causal autonomy, a region of space-time where local systems can evolve, according to their own logic without being instantly overwhelmed by influences from across the cosmos. Several philosophers and theologians have explored this connection between the cosmic speed limit and the possibility of free will. Hans Jonas, a Jewish philosopher who survived the Holocaust, argued that the finite speed of causation creates the conditions for genuine novelty to emerge in the universe. The future isn't completely determined by the past because information takes time to propagate. There are gaps, delays, windows of opportunity where something genuinely new can arise, something not fully predictable from what came before. John Polkinghorne, who was both a particle physicist and an Anglican priest, suggested that the causal structure created by the speed of light allows both divine providence and human freedom to coexist without contradiction. God doesn't need to micromanage every detail instantaneously. The finite speed of causation creates space for both overall purpose and genuine creaturely freedom, working together rather than competing. Now, to be clear, the existence of a cosmic speed limit doesn't prove free will exists. That philosophical debate remains unsettled, and physics alone can't resolve it. But what the speed limit does is create conceptual space where free will could exist without violating the laws of physics. It creates a middle ground between two extremes, between pure chaos, where nothing follows any rules, and rigid determinism, where the future is entirely fixed by the past. In a universe with instantaneous causation, free will seems impossible. Everything is too tightly interconnected, too rigidly determined by the total state of everything everywhere. In a universe with no causation at all, free will is meaningless. There are no causes and effects, no decisions that lead to outcomes. But in our universe with its finite speed of causation, there's a zone between these extremes where local autonomy is possible, where systems can make decisions based on their own internal state and history, without being instantly controlled by everything else in existence. The cosmic speed limit creates boundaries. It defines what can influence what and when. It ensures that your decisions right now are based on information from your past light cone, the region of space-time that could have affected you, not on information from events that are still outside your causal reach. This temporal and spatial structure might be precisely what's needed for any meaningful concept of choice, decision, or freedom. Think about it this way. If I asked you to make a decision, and that decision was being simultaneously influenced by events happening right now in the Andromeda Galaxy, events you couldn't possibly know about or respond to, would that decision really be yours? Or would you just be an intersection point in an instantaneous cosmic web with no more autonomy than a single pixel in a photograph? The finite speed of light ensures that your decisions are yours, in a meaningful sense influenced by your past, by the information available to you, by the physical state of your brain, but not instantly controlled by every event occurring everywhere in the universe at this moment. There's a causal horizon that protects local processes from instantaneous, distant interference. This doesn't solve the free will problem. Philosophers will continue debating whether choices are truly free or merely complex outcomes of deterministic processes. But the cosmic speed limit does something important. It makes the question of free will at least coherent. It creates a universe where local autonomy is possible, where the future isn't instantaneously determined by the total state of everything everywhere, where there's room for something, consciousness, decision making, choice to operate according to its own local dynamics. Without the speed limit, the question of free will would be moot. With the speed limit, the question remains open, debatable, meaningful. The structure of causality created by light speed doesn't give us free will, but it might be a necessary condition for free will to be possible at all. But this still leaves us with a profound mystery. Why does the cosmic speed limit have the specific value it does? Why 282 miles per second and not some other number? So we've established that the cosmic speed limit exists, that it's fundamental to the structure of space-time, that it protects causality and gives time its direction. But here's a question that might have been nagging at you. Why this particular number? Why does light travel at exactly 299,792,458 meters per second? Why not twice as fast? Why not half as fast? Why this specific value and not some other? The answer to this question touches on the deepest mysteries of existence. Why the universe has the laws it does, why the fundamental constants have the values they have, and whether our universe is the only possible universe or just one among countless others. Let's start with where this number comes from. The speed of light isn't arbitrary. It's intimately connected to other fundamental properties of space itself. Specifically, it's related to two constants that govern how electromagnetic fields behave: the permittivity of free space, called epsilon zero, and the permeability of free space, called mu zero. Permittivity describes how electric fields propagate through empty space, essentially how strongly space itself resists the formation of electric fields. Permeability describes the same thing for magnetic fields. These might sound like abstract technical quantities, but they determine the strength of every electromagnetic interaction in the universe. In the 1860s, James Clerk Maxwell unified electricity and magnetism into a single theory. His equations showed that electromagnetic waves, oscillating disturbances in electric and magnetic fields, must propagate through space at a specific speed determined by epsilon zero and mu zero. When Maxwell calculated this speed using measured values of these constants, he got approximately 310,000 kilometers per second. He realized immediately what this meant. Light is an electromagnetic wave, and the speed of light is determined by the fundamental properties of space itself. The precise relationship is that the speed of light equals 1 divided by the square root of epsilon zero times mu zero. Change either of these constants, and you change the speed of light. So, the question, why does light travel at this speed, becomes, why do epsilon zero and mu zero have the values they do? And this is where things get philosophical. Epsilon zero determines how strong electric forces are. If it were larger, electric forces would be weaker. If it were smaller, electric forces would be stronger. Mu zero does the same for magnetic forces. Together, they control every electromagnetic interaction in the universe, from the forces holding atoms together to the light from distant stars reaching your eyes. But why do they have the specific values we measure? This is one of the deepest unsolved questions in physics. We can measure these constants to extraordinary precision, but we have no theory that predicts what their values should be. They appear to be free parameters, numbers that could, as far as we know, have been different. This leads to what's called the anthropic principle. The weak anthropic principle is fairly uncontroversial. We observe constants compatible with our existence because we couldn't exist to observe any other values. If the constants were different in ways that prevented stars from forming or atoms from being stable, there would be no observers to wonder about those constants. We necessarily find ourselves in a universe that permits our existence. The strong anthropic principle is more contentious. It suggests the universe must permit the existence of observers, that the constants are somehow fine-tuned for life and consciousness. This ventures into philosophical and even theological territory, implying purpose or design, which makes many scientists uncomfortable. But consider what would happen if the speed of light were significantly different. If it were much faster, say 10 times faster than it actually is, then epsilon 0 and mu 0 would have different values, and electromagnetic forces would be much weaker. Atoms would be less stable. Electrons would be more easily stripped away. The complex chemistry that life depends on might not be possible. Molecules might not form. Proteins couldn't exist. DNA couldn't replicate. Life as we know it would be impossible. If the speed of light were much slower, say 1/10, its actual value, electromagnetic forces, would be much stronger. Atoms would be rigid, locked into extremely stable configurations. Chemical reactions would require enormous energies. Stars might not be able to form properly, or they might burn out too quickly. The universe would be a very different place, probably a sterile one, incapable of producing anything as complex as a living cell. The actual value we observe sits in what you might call a Goldilocks zone, not too fast, not too slow, but just right for a rich, complex, life-permitting universe. This value allows atoms to be stable, but not too stable electrons to bond, but not too rigidly chemistry, to be complex and diverse stars, to form and burn steadily, for billions of years, planets to exist, with stable conditions and life to emerge and evolve. If the speed of light were even modestly different, say 50% faster or slower, the universe would likely be dramatically different, possibly lifeless. The range of values that permits anything like our universe is surprisingly narrow. Too fast or too slow, and you get a universe without chemistry, without stars, without the conditions necessary for complexity. This fine-tuning is puzzling. Why should the fundamental constants happen to fall in the narrow range that permits observers? One possibility is pure chance we got lucky. Another possibility is that there's some deeper theory we haven't discovered yet that explains why the constants must have these values, that they're not free parameters after all, but are determined by some more fundamental principle. A third possibility, increasingly taken seriously by physicists and cosmologists, is the multiverse hypothesis. Perhaps there are countless universes, each with different values for their fundamental constants. Most of these universes are sterile, lifeless, unable to produce observers. But occasionally, by chance, a universe emerges with constants in the right range to permit complexity, stars, planets, and eventually life. We find ourselves in such a universe not because of design or fine-tuning, but because only such universes contain observers to find themselves anywhere. This is a selection effect not fine-tuning. If there are a billion universes with randomly varying constants, it's not surprising that at least one has the right values for life. And obviously, we're in that one we couldn't be anywhere else. The multiverse hypothesis removes the need for design or purpose while explaining the apparent fine-tuning of our universe's constants. Of course, the multiverse hypothesis is controversial and difficult to test. We have no direct evidence for other universes. The idea might be untestable in principle, which bothers many scientists who prefer theories that make observable predictions. But it remains one of the most intriguing possible explanations for why our universe's constants, including the speed of light, have the values they do. Here's something interesting. In 1983, the scientific community redefined the meter. Previously, the meter was defined by physical objects. First, a prototype metal bar in Paris, later by the wavelength of specific light emissions. But in 1983, metrologists did something radical. They defined the meter in terms of the speed of light. Now the meter is officially defined as the distance light travels in vacuum in exactly 12999,792,4558 of a second. The speed of light is no longer measured. It's defined. It's fixed by definition at exactly 299,792,458 meters per second. We're no longer asking how fast does light travel in meters per second. Instead, we're using the speed of light to define what a meter is. This reflects a profound insight. The speed of light is more fundamental than our human-constructed units of distance. It's a feature of space-time itself, not something measured in meters. Meters are arbitrary. We could have chosen feet or furlongs or any other unit. But the speed of light is intrinsic to the universe. By defining the meter in terms of light speed, we're acknowledging that the cosmic speed limit is more basic than our systems of measurement. So, is the specific value of the speed of light random or necessary? We don't know. It might be determined by deeper physics we haven't discovered. It might be one random selection from a vast multiverse of possibilities, or it might be the only value consistent with the existence of a stable, coherent universe capable of producing observers. What we do know is that the existence of a cosmic speed limit, regardless of its specific value, is fundamental. It structures space-time, protects causality, creates the arrow of time, and possibly enables the kind of local autonomy necessary for anything resembling choice or consciousness. The universe we inhabit is one where information and influence propagate at a finite speed, creating causal structure, temporal ordering, and the logical consistency we observe. And this brings us to a profound realization. We are not separate from these cosmic laws. We are expressions of them, which leads to the most personal question of all. What does all this mean for you, for human existence, for our place in this vast, strange cosmos? Since the first humans looked up at the night sky, we've dreamed of the stars. Ancient civilizations saw gods and heroes written in the constellations. Medieval scholars imagined crystalline spheres carrying celestial bodies. Modern science fiction writers filled our imaginations with starships leaping across the galaxy, with vast interstellar empires, with humanity spreading among the stars as easily as our ancestors spread across continents. We've always yearned to transcend boundaries, to reach beyond our grasp, to explore what lies beyond the horizon. It's one of our defining characteristics as a species, this restless desire to see what's over the next hill, across the next ocean, around the next star. But the cosmic speed limit says not so fast. The universe imposes constraints on these dreams. Does this mean we're sentenced to eternal loneliness, forever trapped on our tiny blue dot, our ambitions forever confined by the laws of physics? The nearest star to our sun, Proxima Centauri, sits 424 light-years away. That's about 25 trillion miles, a distance so vast it's almost impossible to comprehend. With current technology, our fastest spacecraft would take roughly 70,000 years to reach it. That's longer than all of recorded human history. The people who arrived would be separated from the people who launched by 3,000 generations, unable to remember why the journey even began. Even with tremendously optimistic technology, say reaching 10% the speed of light, which would require energy sources and propulsion systems far beyond anything we have or can foresee, the journey would still take 42 years. That's a human lifetime. The astronauts who left would be old or dead by the time they arrived. At 90% light speed, still technologically distant by centuries, if not millennia, the trip drops to about 5 years. Better, but still daunting. There are no shortcuts, no hyperspace jumps, no warp drives, no magical doorways that let you step instantly from Earth to a distant star. Just the slow, patient crawl across enormous distances at speeds that, while unimaginably fast by human standards, are still painfully slow on cosmic scales. So, how could humanity actually become an interstellar civilization? We've considered several possibilities each, with profound challenges. Generation ships are vessels where multiple generations live and die during the journey. The people who arrive aren't the people who left. They're the great-great-grandchildren born in space who might barely remember that Earth was once humanity's home. The psychological and social challenges would be immense. How do you maintain purpose and cohesion across generations? How do you prevent social collapse when the destination is centuries away and nobody alive remembers the world you left? Cryogenic freezing offers another possibility. Put the crew into suspended animation, wake them when you arrive. But despite decades of research, we have no working cryogenic technology for humans. We can freeze cells, even some small organisms, but preserving and reviving a complex human body without catastrophic damage remains firmly in the realm of speculation. It might be possible someday. It might not. A more radical idea: send frozen embryos along with artificial intelligence. The AI guides the ship, builds habitats upon arrival, and raises the embryos into the first generation of colonists. You're not sending people. You're sending the seeds of people, letting them grow at the destination. This seeding approach could spread humanity across many worlds without requiring vast generation ships. But it raises profound ethical questions about bringing people into existence on an alien world with no human parents, no human culture, except what an AI can provide. And then there's the most speculative possibility: mind uploading. Convert human consciousness into data, transmit that data at light speed as a radio signal, and reconstruct the person at the destination using molecular assemblers or some other advanced technology. Your body doesn't make the journey, just the information pattern that defines your mind. But is the reconstructed person really you, or just a copy while the original dies? Philosophy and physics collide in uncomfortable ways. Every option involves compromise risk and questions that go far beyond engineering. But suppose we overcame all these challenges. Suppose humanity did establish colonies on other stars. Even then, the cosmic speed limit would fundamentally shape the nature of any interstellar civilization. Imagine a human colony around Proxima Centauri. Communication with Earth would have an 8-year round-trip light delay, 4 years for a message to arrive, 4 years for the response to come back. There would be no conversations, no real-time coordination, no back and forth dialogue. Every exchange would take nearly a decade. You'd send a question and wait years for an answer. By the time you received a response, you'd have forgotten the context, moved on, or died. This means any interstellar colony would necessarily be autonomous. They couldn't wait for instructions from Earth. They couldn't consult with home about urgent decisions. They'd have to make their own choices, develop their own culture, become their own independent society. The light speed delay would create not just physical, but also political and cultural isolation. The dream of a galactic empire, a unified civilization spanning thousands of stars governed from some central capital, is impossible. Not difficult. Impossible. The distances are too vast, the communication delays too long. Each star system would be its own isolated pocket of humanity, separated by years or decades of travel time and communication delay. Any attempt at central control would be futile. By the time orders arrived, the situation would have changed beyond recognition. The cosmic speed limit creates fundamental isolation between the stars. It's not just that travel is slow, it's that causality itself has light speed delays built in. Events at Proxima Centauri and events on Earth are in each other's elsewhere region for 8 years. They cannot influence each other in real time. They're causally separated, living in parallel timelines that only sync up after years of delay. But there's a strange comfort in this limitation too. The same speed limit that isolates us also protects us. Suppose a gamma ray burst erupts from a star 1,000 light years away. This is a catastrophic event that could sterilize any planets in its path. But we'd have 1,000 years of warning. The light showing us the explosion would arrive at the same time as the deadly radiation. Nothing can hit us faster than light. There's always a buffer, always advance notice, equal to the distance divided by light speed. A nearby supernova, an asteroid on a collision course, visible from afar, even a hostile alien civilization, none of them can strike without warning. The cosmic speed limit ensures we always have time to see threats coming, at least in principle. It's a shield as much as a cage. This brings us to the search for extraterrestrial intelligence. For decades, SETI researchers have been listening for radio signals from other civilizations. It's a beautiful idea, scanning the stars for messages, hoping to find we're not alone. But the cosmic speed limit shapes what this search means. Any signal we detect is ancient history, a message from a civilization 1,000 light years away was sent in the year 1025 AD, while humans on Earth were in the Middle Ages, before the Renaissance, before the Enlightenment, before everything we think of as modern civilization. That civilization might not even exist anymore. They might have destroyed themselves, evolved beyond recognition, or simply moved on, we'd be receiving a message from their distant past. And if we replied, our response wouldn't reach them until the year 3025 AD. The conversation would take 2,000 years for a single question and answer. That's not a dialogue. It's more like an exchange of letters across millennia, each message, a bottle thrown into an ocean of time, hoping someone on the other shore might someday find it. This might help explain the Fermi paradox physicist Enrico Fermi's famous question: if alien civilizations exist, where are they? If the universe is full of life, why haven't we seen any evidence? Why no vast interstellar empires, no megastructures, no obvious signs of intelligence reshaping the cosmos? Part of the answer might be the cosmic speed limit. Interstellar travel is so difficult, so slow, so expensive in energy and time that perhaps most civilizations never bother. Perhaps intelligent life is common, but interstellar civilizations are rare because the speed of light makes expansion across the galaxy impractical. Perhaps there are millions of civilizations out there, but they're all islands, isolated by the sheer scale of space and the finite speed of causation, unable to communicate or visit each other in any meaningful way. We might not be alone, but we might be effectively alone, surrounded by others, yet unable to reach them, like people living on separate islands in an ocean so vast that boats can barely cross it. The cosmic speed limit doesn't just isolate stars. It isolates civilizations, each one developing in its own bubble of space-time, its own causal horizon, its own local reality. So, what does all this mean for humanity's future? Are we trapped, doomed to remain forever on Earth? Our dreams of the stars crushed by the laws of physics? Not necessarily. The cosmic speed limit constrains us, yes, but it doesn't eliminate possibility. It just changes what's possible. We can still reach the stars. It will just be slow, patient, multi-generational work. We can still spread across the galaxy. It will just take millennia, not years. We can still search for other life. We'll just have to accept that any contact will be more like archaeology than conversation, more about understanding the past than building relationships in the present. The cosmic speed limit defines the conditions of existence for any spacefaring civilization. It's not a wall to break through. It's the shape of the landscape we're navigating. You can rage against a mountain, or you can learn to climb it. You can curse the ocean, or you can build boats. The speed of light is like that, not a prohibition, but a fact, something to work within a framework that shapes but doesn't destroy our ambitions. And in a deeper sense, the cosmic speed limit connects us to the universe in ways we might not have realized. Because you're not separate from these cosmic laws, you are their expression, a pattern of matter and energy shaped by the same forces that govern everything from quantum particles to galactic clusters. Stop for a moment. Look at your hand. Right now, hold it up in front of you and really look at it. The atoms that make up your skin, your bones, the blood flowing through your veins, every single one of them was forged in the heart of a star that exploded billions of years ago. That star lived for millions or billions of years, fusing hydrogen into helium-helium, into carbon-carbon, into oxygen, building up heavier and heavier elements in its core. And then, when it had burned through all its fuel, it collapsed and exploded in a supernova, one of the most violent events in the universe. In that explosion, the atoms that would one day become you were scattered into space. Light from that explosion traveled through the cosmos at exactly 299,792 kilometers per second. Not faster, not slower, always at precisely that speed for millions or billions of years. That light carried the announcement of the star's death across vast distances, and the matter, it drifted through space, eventually gathering with other matter pulled together by gravity forming clouds that collapsed into new stars, new planets. One of those planets was Earth, and from that matter eventually came you. Every atom in your body has a history that stretches back billions of years and across billions of miles. You are made of star stuff, as Carl Sagan famously said. But more than that, you are made of matter whose very journey to Earth was announced by light traveling at the cosmic speed limit. The speed of light isn't just some abstract number. It's woven into your personal history, into the history of every particle that makes you who you are. Consider what happens every morning when you step outside and feel sunlight on your face. Each photon touching your skin just completed an 8-minute journey from the sun's surface. But that photon's story is much older. It was created in the sun's core about 150 million years ago, trapped in a dense maze of matter, bouncing randomly from atom to atom, taking tens of millions of years to fight its way from the core to the surface. And then, finally, breaking free, it raced across 93 million miles of space in just 8 minutes, traveling at exactly the speed of light to strike your retina. In that moment, the photon is absorbed by a molecule called rhodopsin in your eye. This triggers a cascade of chemical reactions, converting light into electrical signals that travel along your optic nerve to your brain, and you experience that sensation we call seeing light. The photon's journey ends, but it connected you to the sun, bridged 93 million miles of space, and brought you energy that originated in nuclear fusion at the sun's core, all governed by the cosmic speed limit. Every second of your life is shaped by this limit in ways you probably never think about. When you pull out your smartphone and open a map app, the GPS chip inside is performing calculations that account for Einstein's relativity. The satellites overhead are experiencing time at a slightly different rate than you are, and the software must correct for this using the equations we've been discussing. Without these corrections, without accounting for the cosmic speed limit and its effects on space-time, your position would be wrong by miles. Every text message you send travels as an electromagnetic wave, propagating at light speed through fiber optic cables or through the air to cell towers. Every photograph you take is captured by photons striking a sensor at light speed, their wavelengths and energies determining the colors and brightness of the image. Every screen you look at emits photons that travel to your eyes at light speed, creating the illusion of images and text. You are living within and because of the cosmic speed limit. It's not some distant abstraction that only matters in particle accelerators or at the edge of the universe. It's here now, in every moment of your existence. The colors you see exist because of electrons dancing around atomic nuclei at significant fractions of light speed, their relativistic effects determining which wavelengths of light get absorbed and which get reflected. Every breath you take involves oxygen molecules binding to hemoglobin in your red blood cells through electromagnetic forces that propagate at light speed. Every thought in your mind is carried by electrical signals racing along neurons, signals constrained by the same cosmic speed limit that governs everything else. The chemistry of your body, the electricity of your nervous system, the light entering your eyes, the heat radiating from your skin, all of it operates within the framework defined by the speed of light. You couldn't exist in a universe with a different speed limit because the chemistry that makes life possible depends on the specific value we observe. Here's a profound realization: you are not in the universe. You are the universe, not metaphorically, but literally. You are a complex pattern of matter and energy organized in a particular way, following the same laws that govern everything, from the smallest quantum particles to the largest galactic clusters. The laws of physics aren't rules imposed on you from outside. They're the description of what you are, how you function, why you exist. The cosmic speed limit, that fundamental constant woven into the fabric of space-time, is as much a part of you as it is a part of light itself. Your atoms couldn't hold together without it. Your brain couldn't process information without it. Your eyes couldn't see without it. Every aspect of your existence depends on this limit having exactly the value it does. What you call a limitation is actually the foundation of possibility. If the speed of light were different, atoms wouldn't be stable. Chemistry wouldn't work the way it does. Stars wouldn't form or wouldn't burn steadily. Planets wouldn't exist in configurations suitable for life. You wouldn't be here to wonder about any of it. The cosmic speed limit isn't a barrier preventing you from doing things. It's the ground on which you stand, the framework that makes your existence possible. This is the paradox. The thing that seems to limit us is actually what enables us. The speed of light constrains how fast we can travel. Yes, but it also creates the stable, coherent, causally consistent universe in which complexity, life, and consciousness can emerge. It's not a prison. It's a foundation. On a clear night, go outside and look up at the stars. Each point of light you see represents photons that traveled for years, decades, or centuries at the unchanging speed of light to reach your eyes tonight. You're not seeing the stars as they are. You're seeing them as they were when that light left them. You're looking into the past, witnessing history written across the sky in light. The nearest stars show you the past of 4 or 5 years ago. More distant stars show you decades or centuries past. The faint smudges of distant galaxies reveal light that's been traveling for millions or billions of years. You're not just looking at space, you're looking through time, watching the living history of the universe unfold at exactly the speed limit that makes history possible. Every photon that enters your eye tonight traveled across unimaginable distances without ever slowing down, without ever speeding up, maintaining that perfect constant velocity mandated by the geometry of space-time itself. And in that constancy, in that absolute unchanging speed, lies the stability of reality. The cosmic speed limit isn't about limitation. It's about connection. It connects space with time, weaving them into the unified fabric of space-time. It connects mass with energy, revealing them as two forms of the same fundamental quantity. It connects cause with effect, ensuring that causality flows in one direction, that actions have consequences, that the universe makes logical sense. It connects the past with the future, creating the flow of time that allows change, growth, evolution, and life. And it connects you to the cosmos in the most intimate way possible. You are made of atoms forged in stars. Those atoms are held together by forces that propagate at light speed. Your body runs on chemistry, governed by the same electromagnetic constants that determine light's velocity. Your eyes see by capturing photons. Your brain processes information at rates constrained by the cosmic speed limit. Every moment of your existence is shaped by this fundamental constant in the absolute constancy of light speed in its unchanging universal frame. Independent value lies the stability that makes reality comprehensible. And within that stability, you exist. You think. You wonder. You look up at the stars and ask why. The next time you see sunlight streaming through a window, remember those photons traveled for 8 minutes at exactly light speed to reach you. The next time you look at the stars on a clear night, remember you're seeing the past, touching the present history, arriving at light speed. The next time you think about limitations, remember the cosmic speed limit isn't what prevents thought. It's what makes thought possible. When you feel small in the vastness of the universe, remember this. You are made of star matter, governed by the same laws as everything else, connected to the cosmos through the same fundamental forces that shape galaxies and ignite suns. And in that, there is profound beauty. 299,792,458 meters per second. It's not just a number, it's cosmic truth. It's the boundary between reality and chaos, between causality and paradox, between logic and absurdity. And within that boundary, we find not imprisonment, but freedom. Not limitation, but possibility. Not an ending, but the beginning of understanding. This cosmic speed limit defines the shape of reality itself. It ensures that effects follow, causes that time has direction, that space has structure, that the universe remains logically consistent. It creates the conditions for stars to form, for planets to orbit, for chemistry, to flourish for life, to emerge for consciousness, to wonder about its own existence. You are not separate from this cosmic architecture. You are an expression of it. Every atom in your body, every thought in your mind, every beat of your heart occurs within the framework defined by the speed of light. You are woven into the fabric of space-time, subject to the same laws as photons and planets and galaxies. And in that fact lies a connection more profound than any philosophy or religion has imagined. When physicists say the speed of light is the cosmic speed limit, they're not just describing a rule about motion. They're describing the fundamental structure of existence, the framework within which everything happens, the stage on which the universe plays out its grand drama. And you're not just watching that drama, you're part of it. You're a character in the story the universe is telling itself. The cosmic speed limit isn't about what you can't do. It's about what you are. It's about the nature of space-time matter, energy, causality, and consciousness. It's about the structure of reality at its deepest level, and understanding that really grasping what the speed of light means is to understand something profound about the universe and your place within it. So the next time someone asks you why nothing can go faster than the speed of light, you can tell them it's not really about speed at all. It's about the nature of space-time. It's about the relationship between cause and effect. It's about the framework that makes reality coherent and comprehensible. It's about the boundaries that define what's possible and what's not. And it's about the connection between the smallest particles and the largest structures, between the shortest moments and the deepest time between you and the cosmos. In the end, the cosmic speed limit teaches us something beautiful. We are not separate from the universe. We are the universe looking at itself, made of star atoms bound by light speed forces, experiencing reality from within the very framework we're trying to understand. The speed of light doesn't just describe how fast light travels, it describes the fundamental nature of existence itself. And that's the answer to our question. Nothing can go faster than the speed of light, because the speed of light isn't a speed limit. It's the conversion rate between space and time, the fundamental constant that defines how reality works. It's woven so deeply into the structure of the universe that asking why nothing exceeds it is like asking why circles are round or why triangles have three sides. It's not a rule imposed from outside. It's part of what reality means. Thank you for joining me on this journey through one of the universe's most profound truths. We've traveled from the observations of a Danish astronomer in 1696 to the cutting edge of modern physics, from laboratories to philosophy, from mathematics to meaning, from the smallest particles to the largest galaxies. And we've seen how everything, absolutely everything, is connected by a single constant, the speed of light. If you found this story fascinating, there are countless other mysteries of the cosmos waiting to be explored. The universe is full of wonders, black holes that bend space-time into impossible shapes, quantum mechanics that suggests reality isn't quite real until you observe it, dark matter and dark energy that make up most of the universe yet remain invisible to us. Each mystery is a door waiting to be opened, a question waiting to be asked. But for now, we end here with this simple truth. 299,792,458 meters per second isn't just the speed of light. It's the heartbeat of the cosmos, the rhythm that underlies everything that exists, the constant that makes reality itself possible. And you are part of that reality, living within it, shaped by it, connected to everything through it. The cosmic speed limit doesn't confine us, it defines us. And in understanding it, we come closer to understanding ourselves and our place in this strange, beautiful, logically consistent universe we call home.